reliability assessment for bidirectional single-stage DAV-based three-port photovoltaic energy storage inverter, and presented by Mr. Guanyu Wang. He is currently working toward the doctorate in electrical and electronics engineering from Xi'an Jiedong Liverpool University, Suzhou, China. He received the Bachelor Engineering degree in electrical engineering from the Northeast Electric Power University, Jilin, China in 2018. And he received the Master of Science degree in Sustainable Energy Technology from Xi'an Jiedong Liverpool University, Suzhou, China. In 2021, he is currently working toward the doctorate in electrical and electronic engineering. His research interests including control of DC to DC, DC to AC converter, three-port photovoltaic energy storage inverter, and bidirectional switch. So please give him applause for the presentation.
Okay, thank you all for listening to my presentation. The title of my presentation is Analyze and Reliability Assessment of Bidirectional Single-Stage DAV-based three-port photovoltaic energy storage inverter. I am Guangyu Wang from Xi'an Jiedong Liverpool University. Thank you all. My presentation has been widely divided into 5 parts. First is the background, and then briefly introduce of the proposed technology, and then is the work mode analyzed, reliability analyzed, and then the last is the simulation result. Now let's move on to the background. In recent years, the carbon naturally has been well known by us. There are more and more researches on the new energies, especially solar energy and wind energy. But this new energy has some disadvantages. It cannot generate the power smoothly. So it is necessary to use a battery to storage the energy. And when we need the energy, we use both. We can get the energy from PV and the battery. The traditional power electronic system is shown on the left corner. It has 2 DC-DC converters, so it has a high cost and low efficiency and low reliability. So here comes a 3-port converter system. It can connect the PV and battery and the bus together. And here is the proposed topology. It has 2 sides, DC side and AC side. The battery is connected to the port 1, and the PV is connected to the port 2. And AC bus is connected to the port 3. The DC side is a full bridge, and 2 additional inductors connected the PV and the high frequency transformer. And it is a half bridge on the AC side. 2 bidirectional switches are on the both bridge arms. When 2 ports work together, there are 3 working modes of this topology. The first one is the port 1 and port 3. At this time, the power can transfer from the battery to the AC grid or the AC grid to the battery. And the second working mode is port 1 and port 2. At this time, power transfer from PV to the battery and storage the energy. And the last one is port 2 and port 3. At this time, energy transport from PV to the AC grid. Now let's analyze the first working mode. At this time, the key waveforms are shown on the left. The 4 switches on the full bridge are controlled by SPWM wave. And on the AC side, bidirectional switches are controlled by a modulated wave with a duty cycle of 50%. But it is, but on the AC side, to reduce the power loss and improve the life of this bidirectional switch, there are two switches normal on when AC is in the positive half cycle, and the other two switches normal on when the AC is on the negative half cycle. And the second working mode is port 1 and 2. At this time, we can see that the topology worked as an interleaved boost converter. And S1 and S4 turn on and off at the same time, and S2 and S3 turn on and off at the same time too. The duty cycle is 50%. And the last mode is the port 2 and port 3. At this time, we can combine two working modes together. It can be seen we boost the voltage from PV to the capacitor 1, and then the energy transfer from capacitor 1 to the AC load. And here is the topology. We can see that when the AC if we saw one bridge arm is a cell, we can find that if AC side is working, it is all three cells must included in the power cycle. But when it's working in port 1 and 2 mode, the interleaved boost, if any arm breaks down, it can also work as a boost converter. So if any switch is broken, this topology can keep on storage the energy generated by PV to the battery. So it has a higher reliability. And here is the reliability form from the handbook. From left to right is the basic Fourier rate and the effect of temperature usage and the quality of the power supply and the strength of power supply and the connection and the quality of the switch and the environment. High T can be more expressive by the temperature of its use. It can be explained by other in different temperature we used and different power. And I also can further express as the voltage and current the topology is under. And other can be found in the handbook. So we have the and we can get the relationship. We can based on the relationship between the Fourier rate and its reliability. We can get the reliability of this whole topology, and then we can get the mean time to failure to get what is the reliability of this whole topology. Here we can get the reliability. We can see that the proposed topology the reliability of the proposed topology is higher than the traditional one under any power and in any time. So this topology is better than the traditional one. Okay, and at last is the simulation result. Here is the parameters of this all components of the topology, and here is the key simulation result and the this is all of my presentation. Thank you all. If you have any question, please feel free to ask. Thank you.
Okay, to open the floor for any questions. Okay, no questions. So let me ask you. It's kind of interesting that you like remodel of the conventional bidirectional into the three part, right? So once we study, like right now it's in the simulation, right?
Yeah.
So once move up to the hardware, the real test, did you plan to do that in the next your future work?
Yeah.
Yes. So how do you think about the data of the when you like control very short term and you need to use the switch, like only limited switch, right? Because it's reduced.
Yeah.
So what do you think about once anything need to more flexible or any plan if what problem, what kind of problem that you're gonna face, you think? Like probably is that any consideration that we need to plan? Like we move up from this idea into the real test.
The real test, you can say that when we completely change the power, the load demand or the direction of transmission, it is not that good. So we can improve it from the control. The control of this study is not that good. So here is a point can improve this, and the load of from this body, it is not grid connected. We simulated the grid, but it's not a real grid. So the grid may have some effect on this, but that is further study on this.
Next, that's good, that's interesting. All right. So any question? No question? So thank you very much for your presentation. Thank you. And next is the paper title, State Estimation in Power System under Deterministic False Data Injection Attack Using Minimization of Nuclear Norm and L1 norm with noisy constraint substitution.
Sorry, I provide the file in PDF form, but I cannot find on the screen right now. It's in PDF format. I have Line. Okay. Is it possible to use Line, transfer the file? doesn't work.
Not work.
How can, okay. Oh, doesn't go. Or you have HDMI connector, this type C.
I don't have HDMI.
Is it possible I transfer the file to you and you send it to this?
Add frame. Add frame. Select. Đi vào đó. ID line.
Okay. Underscore.
ไม่ได้เอาไฟล์มาต้องเชิญท่าน
ครับส่งไปแล้วเหมือนกันครับ
ไม่มีลงใน
ส่ง
ที่นี้นะ
ส่งไปในเมลครับ ให้กับที่ของคอนเฟอเรนซ์ไปแล้วครับ ทั้ง2 ไฟล์เลยครับ แต่เขาไม่ได้เอามาไว้ที่ครับ underscore ตรงไหนครับ underscore โอเค yes อันนี้ครับเดี๋ยวส่งไปให้ครับไม่เห็นครับ
เดี๋ยวผมทักไปเลย
สติ๊กเกอร์อะไรครับ
นี่นะครับนี่เมื่อกี้
นี่นะครับ
ใช่ครับ
โอเคครับอ๋อ where is that this one อยู่ตรงไหนครับอ๋อไปแล้วครับ
สองไฟล์เลยครับ
อันนี้มันสปีกเกอร์ฟอร์มจะส่งให้อาจารย์ครับ
อันนี้ยังไม่ส่งให้นะผมยังไม่ส่งอะไรนะครับ
ไปแล้วไปแล้วนะปิดอันนี้ยังไงครับโอเค sorry for the inconvenience okay good afternoon everyone welcome to my presentation the topic is quite long my name is Bamrung Tausi School I'm going to be the presenter of this work it's about state estimation in power system under deterministic false data injection attack using minimization of nuclear norm and L1 norm with noisy constraint substitution. Okay, the content in this work is as follows. We are going to talk about electric power systems, measurements in electric power system, state estimation problem in power system, and we will talk about the recent issue in power system when someone tries to attack the wrong data or the false data. It's called a false data injection attack. And we're gonna give a review to you regarding the minimization of the nuclear norm and air1 norm with noisy constraint. After that, we will see the proposed optimization technique using constraint substitution. And then we see the numerical example from the computer simulation. And finally, we're gonna talk about concluding remarks. As you know, in electric power system, we have several steps like generation step and increase the voltage, and then we have a transmission process in distribution area here. In order to monitor the power system, we need to measure some quantities, for example, voltage magnitude, current flow in terms of magnitude or injection, and active and reactive powers. And maybe sometime we want to know also synchronized phasors from PMU or phasor measurement unit. The tools for measuring the quantities in the electric power system is the following. We may use multimeters, we may use PQ data loggers, oscilloscope, disturbance analysis, spectrum, and harmonic analysis or PQ analysis. Well, regarding the state estimation, this is the distribution system. There are several transmission lines and buses. They are connected to control units that has the task like state estimation or load distribution. And there will be a person who would monitor what's going on in the whole system. State estimation is a task that tries to extract the important state of the power system from the collect data in this network. Well, but in modern technologies, because we are in the digital era, someone who is not good tries to attack our system by injecting the false data. So this will raise the difficulty in the state estimation in the power system. Regarding the attack, it can be classified into denial of service. It means someone say the wrong information, sends the wrong information. For example, the generator doesn't work, but actually it works. Okay, this is denial of service. Another kind of attack is replay. It means someone capture the data and then they are not authorized, and then they use our information and they try to destroy the whole system. But the attack that we will consider in this work is false data injection. So someone tries to inject the wrong data to the system. So the power state estimation is going to be more difficult. Regarding the mathematical model, you have the typical model of linear power state system like this. Okay, this is the measurement Jacobian matrix, and this is the state vector. That's the parameter we would like to know. And there is an additional additive noise in due to the unintentional person, there is an attack component here. And Y is the measured data that we receive from the measurement unit. So our target is to find theta, but what we could observe from the attack model is only theta with tilde, which is the wrong one. Well, someone has already, previous work has already presented the idea in order to get back the desired signal component, which is Z0. They separate the received data Y into three components, the desired signal, the attack component, and the additive noise. Okay, the idea is that they try to minimize the nuclear norm of the desired signal and the L1 norm of the attack. We assume that the attack component is sparse or some elements in the attack contain zero, has zero. So and we minimize also the noise in the Euclidean sense or norm 2 with a constraint like this, which is the former observation model. This is the equality constraint, and you can see that the optimization framework here is quite complicated. And the idea in this work is that we try to simplify this problem, this optimization problem, into a simpler one by substituting this constraint into the objective function here. Okay, you can see that if we arrange the noise term, we can get this relation for the noise, and then when you substitute n or noise into this objective function, the third term in the objective function, you can get the unconstrained optimization, which is simpler than before. So the difference between this work and the previous work is the following. Both problems are convex, and we can use commercial software that is available in many places. And in the previous work, the problem has a constraint. But in our problem, once we substitute already the constraint, so there is no longer constraint anymore. And the search dimension in the previous work is 3 times m. M is the number of measurement devices that you want to monitor the system. NT is the time sample that you want to observe according to the time. And in our proposed technique, the search dimension is reduced by 1/3. So the remaining thing is 2 times m and NT. Regarding the simulation result, you can see that this is the normalized bias norm, and when the signal is stronger, it means the signal to noise ratio is the SNR increases. So you can see that the previous method and the current method provide exactly the same error in the first order sense. It means the bias, the error of with the power of 1. And when you observe the error in the second order, it means root normalized mean square error. When the SNR increases, both methods provide the same error. And regarding the standard deviation mean, how the solution is far from the mean. So both are still provide the same performance. So you may be wondering what is the benefit from this work in this figure. Our method consume less computational time, elapsed time in computation. The circle one here is lower than the plus sign from the previous work, because we reduce the optimization search dimension. So the conclusion of this work is that we propose an improved optimization technique to extract the desired signal component from the attacker data from the measurement. And the numerical result indicate that our proposed provide exactly the same error performance, but it takes less computational time than the former work. And that's it for our presentation.
Any question? Okay.
It's very good presentation that you deal with false data injection or FTI that relate to cyber attack or something like this in nowadays. But in your technique, did you deal with something that more a little more advanced than that they call the denial of service (DOS). That it is cut the signal of the component that you can deal with. Have you dealt with this problem?
I didn't address this problem yet. Most of the literature pay attention to these thing, false data injection. Most of them work on this category. So maybe I will switch to this one. What do you mean? They stop sending.
You cannot. They block the communication. The way of you where you put the FDI, they cut down that channel, and you cannot communicate with your system. So this now they try to interrupt that part by maybe add a lot of data, the data, flood the system to be cut away, something like this. So it's called denial of service. You cannot have that service anymore. So I think I just read about this field of cyber attack, and it's interesting that they have false data injection, denial of service, and one more thing that in industrial they try to hack the controllers. They call controller hijacking. They have the controller of the in factory, and they change the parameter that the controller cannot work well, and is go to the system collapse, something like this.
Okay. Thank you very much for the broader view, so that I can change the research area.
Thank you.
Any question? Please. Thank you for this question. Next question, please.
Regarding these false data injection attacks, if the magnitude of the attack is very less, it can lie very close to the system healthy states. So in such type of attack, will your method be able to detect? If the magnitude of the attack, suppose you are injecting some kind of data, a false data injection attack, that if the magnitude of that magnitude is very less, it will lie very close to the healthy system states. So in that case, will your method, we will be able to detect it?
As I correctly understand what you mean, if the attack has a very small contribution, right? When A is very close to zero, how can we detect the desired signal or detect the attack, right? Well, in this work, I didn't consider detecting the attack component or the desired component. The purpose of this work is that we would like to find theta that is hidden in desired signal component and the attack. We didn't remove the attack at all from the data. We still try to find the state vector even the attack is present. But there are also some works that deal with what you mean. They try to detect the attack and the desired component. But actually, if you look at this optimization framework, they classify the signal into desired signal, attack-free component, attack component, and the noise. Okay, they have 3 components already in here.
Okay, one more thing. You have reduced in your method, you have reduced the computational complexity. Okay, that's good. But still, it requires iterative kind of solving the system. If the system scale is very large, will it be compatible in real time? Its online operation is still implementable.
This is a question. I didn't try like the bigger system, for example, I&CPS 39 bus and so on. The size that I use in this figure is 3 by 2. 3 by 2 mean the H matrix, the Jacobian matrix here has the size 3 by 2. Three measurement devices and 2 components in the state vector. But now we are setting up the experiment in our laboratory with the real hardware. We are going to do something like I don't need 39 bus. Then maybe in the future I will tell you. But from what I expect, the complexity increased exponentially. So it would take much, take much more time.
Let me ask you a quick question.
Yes, please.
I think it's interesting, like you put the substitute one function in order to like simplify,
Yes.
right?
Yes.
But once we do like that, and do we lost some degree of estimation or something, or
No, you still can find the whole three vectors. You lost. But here you can get only desired signal component and attack component, and we cannot find the noise component at all. But the noise is not of our interest at all. Because we want to get only desired signal component, we use this component to get the state vector.
So it's the intention that you don't need any of those noise.
Noise is not important for us, actually. Yeah.
All right. So, no any other questions? So I would like to thank you very much.
Thank you.
Please give him the applause round. Thank you. Okay, we're gonna move to the next presentation. The title is Nodal Price Forecasting Based on the Spatial Temporal Transformer, presented by Mr. Chan Kang Chen. He received the bachelor degree in robot engineering from Peking University, Beijing, China in 2023. He is currently working toward PhD degree in industrial engineering and management with the College of Engineering, Peking University, Beijing, China. His research interests including machine learning and data valuation.
Based on spatial temporal transformer. As we know, accurate shown in the lower figure, with equal connections applied between these two parts to enhance the model's learning capability. Then let's take a closer look at the spatial transformer. Since transformer cannot directly capture the positional information from the input, a positional embedding is required to inject positional information to the input data. To this end, we introduce a learnable spatial embedding layer to fuse the positional information into the input. The embedding layer can capture underlying spatial relationships. Then we can concatenate the initial input and the positional embedding to form the embedded input for the self-attention layer. In the spatial transformer, we apply a self-attention mechanism to the embedded input. The embedded input are mapped to query, key, and value, which are QS, KS, and VS here, through three matrices, WS, Q, WSK, and WSV. Then QS and KS are field productive. Softmax is applied to the result to determine the weight for VS, and we can get the weighted sum as. Finally, a feed-forward layer follows after the weighted sum. To conclude, the spatial transformer helps the model learn the importance of different spatial locations relative to each other. And skip connection is also applied within the spatial transformer after the feedback layer. Now turning to the temporal transformer. It attends to the temporal dimension using a sine-cosine temporal embedding layer to fuse sequential information. Similar to the spatial transformer, it employs self-attention mechanism and skip connections to effectively capture temporal dependencies. As for the experiments, we conduct two experiments through using data from the California Independent System Operator day-ahead market for the year 2018 and 2021. In both datasets, we use hourly node prices from the past 7 days to predict prices for the next day, and at 10 and 8 nodes respectively. And to demonstrate the performance of our model, we compare it against several baselines, including naive prediction, which means we just use the price of the previous day as prediction, and lasso, ANN, LSTM, GRU, and a TCN, GCN-based autoencoder. These models represent a range of traditional and advanced techniques in machine learning and deep learning. As for the matrix, we use root mean square error, which is RMSE, mean absolute error, which is MAE, and symmetric mean absolute percentage error, which is SMAPE. These matrices provide a comprehensive assessment of prediction accuracy, which are defined as follows. First, we evaluate the performance of each model on both datasets. Our results show that the spatial temporal transformer outperforms the baselines on all three matrices. Specifically, our model exhibits lower RMSE, MAE, and SMAPE for both the 2018 and 2021 datasets, highlighting its superior ability to capture spatial temporal dependencies. Second, we randomly choose some periods on the test set to perform the prediction task and plot the predictions of our model and other baselines. Due to the limitation of the frame, we only display 1 day and 4 nodes in the dataset of 2021. Analyzing the predictions, we find that the baseline models tend to overestimate or underestimate node prices, while the ST transformer can perform better. Moreover, the baseline machine learning and deep learning models are more likely to predict a similar output for all nodes, thus leading to a larger prediction error for an abnormal node. For example, the upper right one. For cases like this, the spatial temporal transformer can still perform very well. Finally, to have a better view of the prediction error during the predicted day, we plot the average prediction error of each hour of a day. The mean absolute prediction comparing the hourly MAE curves of different models, we can see that the spatial temporal transformer consistently shows lower prediction errors, especially during the peak hours, indicating its robustness in handling high variance periods. In conclusion, we utilize the spatial temporal transformer model and it effectively predicts node prices by capturing complex spatial and temporal dependencies. Experimental results on real-world datasets confirm its superior performance over some existing baselines. As for future work, we hope to apply our model to more various datasets and scenarios. Moreover, to tackle the problem of the O(n)² computational complexity of transformer, our future work may include incorporating sparse mechanisms to reduce the complexity of the transformer, making it more efficient for long sequence and larger networks. Thank you for your attention, and I'm looking forward to your questions and feedback.
Any questions?
What is the application of this nodal price forecasting? Means what is the need of it?
We use our model on the dataset on the castle dataset, and we think the main purpose of our model is to predict the node price, and it can help, for example, the consumers or the electricity traders or something like this. For it maybe include power generators. If they can predict the electricity price better, they can determine how they should generate electricity in the next day, and thus they can make more profits. That's all.
Because you are considering some kind of data set. That means we already have the prices. So you are using the same data set for prediction. So means how you are concluding that your prediction is good, because data set is already available. We are using the same data to predict. And what is the next step after prediction?
Maybe it involves some maybe, for example, in our one of our projects, we use the we predict the electricity price for a company called in China, and the predictive prices can help them better decide how they will generate electricity in tomorrow's production.
Okay, thank you.
Any feedback? Any questions? Okay. So let me ask you a question, please. When you have the choosing a pickup like weighting factors in the model, right?
Oh, yeah.
And how you like comes up with those numbers?
You mean this model? Firstly, the depth, the non-layers, or just like this. One of the most important parameters is the number of the spatial temporal blocks. If the spatial temporal block, the number of spatial temporal transformer block is small, then maybe we cannot capture the the hidden side of the transformer, for example, Q, K, and Z, and all these dimensions correspond with each other. So we just tune the number of parameters, and we get a good result.
And from this concept, can I like expand to, because the result you show us is like day ahead forecast, right? Just 24 ahead.
You mean how many?
Your forecast, just day ahead, right?
Yes.
So if you like longer, like week or
yes.
you know, can you use this?
In our model, we use 1 week ahead, which is 7 times 24, and that is 168 hours to predict the future 24 hours.
Do we need to modify some of the parameters in the model, or you can use just like that?
Why?
Can be used. So no matter day ahead or week ahead, you can use this concept, right?
But longer time sequence requires a larger
Number
memory.
data set. But that's okay. But other than that, it's fine. Okay, please.
Thank you. I have two questions. Firstly, about you mentioned about the abnormal node. So can you explain more about which node can be considered as an abnormal node, and how about the accuracy if you consider only the abnormal node? And the second question is, you consider the error as the metric, but how about the time consuming consider compared with the other methods?
The first question is abnormal node here. Yes, as you can see, the first, the third, and the fourth node is the tendencies are similar. But in the second node, you can see from maybe in the morning the blue line is the real price, and you can see the real price of the second node is not similar to the other three. But you can see the red line is our model. It can really predict well, and it can follow the blue line. But as for other machine learning or deep learning models, they usually goes just with other nodes and cannot learn the specific trend of this node itself. And as for the second question, you mean the time consumptions? Yes, the spatial temperature transformer do as since the computational complexity and memory complexity of transformer is both O n squared. But as for other models, the time consumption is much. As for ANN, LSTM, and GRU, these models do have less time. But as for deeper neural network, for example, here the TCN plus GCN based model based autoencoder and our spatial temporal transformer. These models, because they have more parameters and they have deeper layers, they do need more time to train. But as for prediction, they work fast.
Thank you.
In your convolutional neural network, you use how many hidden consistent layer and node do you use to model your CNNs?
You mean here?
Yes, your CNN is a convolutional neural network.
Yes, the CNN is mainly used to tune its feature dimensions. For example, when as for the initial input, it only has a node price is one feature, but in but in the neural network, it's a higher dimension. We usually use, for example, 64 or 128 dimensions. So here we only use the one times one kernel to just to increase the dimension, but we do not.
And what is the activation function you use to activate your prediction? Activation function.
The activation to use what? To use the convolution.
For your input, for your output of a CNN, what is the activation function? Tang sigmoid or something?
As for the convolutional layer, we just use the CNN, but we do not use the activation.
Why? If your prediction is really high, so if you did not use activation function, if you not normalize your output, can it still be used?
We use that. We mainly use convolution. We mainly use activation in the second part in our spatial temporal transformer blocks. But as for the star convolutional and convolutional layer, we just our purpose is only to change the dimension. But I think you're right. I think adding activation functions to the end and star convolutional layer will help training and will help the model performance. I think so.
Okay, the last question. So you said that you use two feature to predict the right in I mean input feature. So you use two input feature, right, for your CNN model.
As for you mean
XE and XS and E, right? And the next one. The next. Next one. Here XS and ES, right? This is input feature or not?
yes.
So my question is that if after finishing training your CNN, but if you lost one of these input, one of these two input, can your algorithm still work? For example, you lost XS and you feed only ES to your prediction model. Can it still be used or not? Can you consider this case because it may be uncertainty that your XS may be disappear in maybe some condition in the actual system?
You mean for some parts or for a period of time?
Yes, for some specific period of time.
Yes, I think as for me, I think many data imputation method can be used, and I have read some papers on this. Maybe I haven't tested I haven't tested the performance of our model if when the data is partially missing or something
just a format that you can you may apply to your future to consider
yes.
this problem, right? Thank you.
All right. Thank you for your discussion and thank you very much for your presentation. So let's all give him applause. And we're going to move to the next presentation. The title is Dynamic Assessment of Thailand Available Transfer Capability for Third-Party Access. Will be presented by Mr. Thanakorn Sothiravut. He is graduate student. He got bachelor degree in electrical engineering and right now he is graduate student in Kasetsam University, Thailand.
Okay, thank you very much, Chairman. Good afternoon, ladies and gentlemen. Thank you and welcome to my presentation. The first, let me introduce myself. My name is Nagan Surabut, from Department of Electrical Engineering, Faculty of Engineering from Kasetsam University. My topic today is dynamic assessment of Thailand overall transfer capability for third-party access. Okay, let's go. We're gonna go talk with the agenda. The first, we're gonna go talk with a background and motivation. Second, configuration of Thailand Sun transmission system. And next, we're gonna go with analysis of overall transfer capability (ITC) for third-party access that we call TVA. The last but not least, we'll go with simulation results and at the end with the conclusion. Okay. Let's go with background and motivation. The increased adoption of renewable energy sources has contributed to a more diversified energy market, and the expansion of urban community and increased industrial activity have led to a substantial rise in electricity load demand. Okay, need to investigate the new mention, constraint and cost, multiple facts into transmission system, and the improvement of TVA market system has ensured stability, electricity access for all, significantly reduced the occurrence of outage. Okay, next we're going to go into the objective. First, to analyze power transmission capability in different regions of Thailand under various scenarios, and to evaluate the impact of transmission and ascertain the remaining electricity capacity in each situation. Okay, this picture will show you about the TVA background. At the first, we have to get to its transmission system owner, system operator, single buyer, and we have the MBA and PA, which is distributor and retail supplier. We will expand it next slide. Okay, third-party access or electricity. As I have to explain before, Thailand is this market follow and enhance single buyer model with EGAT, monopolized high voltage transmission and wholesale market, while MBA and PA will control distribution and retail. Access to both transmission and distribution grid to sell power to distant customers. Next, the TVA in the electricity markets allow the companies other than utility for infrastructure owners to use transmission or distribution network, promoting competition. This enables multiple producers and suppliers to access the same network, providing consumers with more choices and potentially lower prices. Alternatively, TVA has benefit. TVA can create a challenge and impact the reliability for the power grid. This is due to the unpredictable behavior of renewable energy sources, which can cause producers to feed uncontrollable amount of the electricity into the grid. Okay, next we're going to go with Thailand transmission system. In this picture, we show the Thailand transmission system that the picture will have Thailand have to be generate power and send it into the urban and regional area. That the picture is so. That means the Thailand transmission system is so essential and must to be maintained. Okay, the next topic we will go to about transmission voltage level. And the ECAT uses various high-volt transmission tower, including 600 kilovolt, but is likely to use and have 150, 230, and 500 kilovolts. High-volt power system can efficiently distribute electricity over the long distances. Okay, we're going to go to next with overall transfer capacity, or we call this ATC. ATC is a measure that's overall capacity in the transmission system for further commercial transaction between power supplier and consumers, and is significantly impact the effective operation of the power markets from both a technical and economic standpoint. Okay, in this picture we show ATC is utilized in the power system of many countries around the world. For example, in this Asia we have in Japan and China, India and Bangladesh. In Africa we have in Nigeria, in other countries in Europe, and in North America, like in the States of America and Canada. Okay, next we're going to go with the rule of the ATC calculation. ATC can be expressed by this equation. And total transfer capacity, or we call it CTC, refers the maximum amount of electric power that can be transmitted over a specific part on the network without violating established electrical constraint. And next, first limit can be a thermal limit, voltage limit, stability limit, and generator limit. But in this our research, we're focusing on voltage limit and generator limit. Voltage limit is mean voltage is used to be between 0.95 to 1.05 per unit, and generator limit is mean generator will not generate the power more than the rated or maximum. Next, transmission reliability margin, or TRM, is a parameter used to evaluate potential future changes in a power system, including variation in demand, loads, and the energy. TRM is typically fixed among the other percentage, which can be various based on the load and generation of each system. Okay, next to the ETC denotes the existing transmission commitment that including CBM, and CBM is capacity benefit margin is the portion of transmission transfer capacity that load is serving entities is reserved to ensure access to generation from interconnect the system, thereby fulfilling generation reliability requirement. Then we're going to go with the ATC computation method. The method ATC computation, we have relative method called active power flow, and reactive power flow, and optimal power flows. They are more accessible and sustainable mentioned for calculating ATC in the large power system. And this we simulation the model on the power factor silence, and we analyze in the equation model of 230 kilovolt system. Okay, this picture will show the physical model of Thailand, and we convert this to the equivalent model to easy to analysis on the right side. Okay, next we're going to go with a simulation result. In the first case scenario, I'll focus on transmitting electricity from the central region to the southern with the red line. Like it have or the southern region want to buy power from the center, it have the only one transmission line to transfer the power that we call in center to southern, or C to S line. And the simulation result, this graph on the left, this will show we increase reactive, active, and reactive power load in the southern region using method that APF and RPF to observe system voltage. And we have the value of the ATC in this slide. This is the trend of ATC value indicates power that transfer from central region to the southern region. And in the second scenario, is in more transmission electricity from the central region to the northern, crucial to the non-rapid economics and industrial growth, despite the sufficient local production capacity. If you see it have two different color of the cross of the arrow. First is directly transfer to center to northern that we call center to north line or C to N, and the green arrow that's run from center across to the northern eastern and northern eastern to the north next that we call C to NE and to N. And the scenario on the left, that we use the same method like scenario 1 to plot a active power and the reactive power, and we have the ATC of two-way directly on C to N in the blue and ATC C to NE to N in the orange. And the third scenario is for the transmitting electricity from the central region to the northern eastern region. Most use electricity from domestic production and import from neighboring countries such as Laos. It has two different color, like on the red that directly sent to center to northeast, and the green is across to the northern, and we go to northern eastern second. And the graph that will show the same method, and we will have the ATC in two color. The blue has the center to northeast line, and the orange will show the center to north and to northern. And the first scenario is for the transmission from the central region to the eastern. Stability, this region is virtual Thailand economic system. ATC calculation involved, it have only one line center to eastern region. And we use the method have to the relationship between active and reactive power with system voltage, and we have the ATC right here on the right. And then in the fifth scenario, in the transmission ACT from the central region to the northern region under the N-1 scenarios, the N-1 criteria plays a crucial role in ensuring the continued operation of the system in the event of the component failure. And in this picture, we have a clause on the one transmission line that we remove. In my research, we have to cut off the line that have more power in the base case, and we will have the central region to the northern region, and we will see the ATC, trade of ATC, that have to increase, value have to increase in some point because central region has to generate the power that enough for the load. Then when we increase load at the same point, that generator cannot generate the power enough that have another region to help, and ATC is linear decreases next. And in the sixth scenarios, the scale will show the change if the generator is northern eastern, it is slack, and by simulating the system transmission electricity. Okay, so we have an E to C to E line and an E to N to C to E line. The ATC have two different colors. And the last scenario also we can show the change generator eastern region is a slack one, and send the power to the southern. So the ATC has decreased on the picture of this. Okay, we go with the conclusion. This table will show the ATC in the higher load and case study in the slide step, and model use data from March to June 2023. Okay, we could go with conclusion. When electricity generation in the region can meet demand, the ATC value decreases because the electricity must be transmitted for another area to compensate for the shortfall in generation is across southern Thailand. Then when they have enough electricity to meet demand, the ATC intensity rise due to less interregional flows. However, it's for when generation becomes insufficient, requiring import for water regions. This occurs in northern, northeastern, and eastern in Thailand. And next, in the N-1 constituency scenarios, electricity can still be transferred between regions, but the ATC reduced because one transmission line has been removed. This reduction requires the distribution load among the remaining lines, resulting in lower ATC values. And the last way the slide one is moved, the trend of the ATC is like to case 1 and 2, considering the balance between electricity generation and demand between the regions. Okay, this is all my research. Thank you for your attention.
question? Any question? No question. So let me ask you.
Okay.
When you like calculate the value like ATC, so once we finish with the number that the result that you show up, so do we cross check like with the provincial authority of Thailand who in charge of those transmission line? Do they have those kind of close by information that can make sure that okay,
This is true, right?
yeah, it's true, or it makes sense, or it's too higher or too low or something?
So that's first is a good question, but we will expand this project. This our research we have calculated at the ATC in steady state. That is mean ATC will be the linear. Yes, but it's good because in the future we can check the power flow that it will be in the dynamic and in the time domain, and we will develop this research to this. Yes.
Yeah, that's good. So it gives you feedback that if you verify some other information from the provincial authority of Thailand, provincial PEA, who take care and in charge of those transmission line around the country, so they might give you some more information and make the model more accurate.
Okay. Thank you very much.
Thank you for your presentation and give him applause for
Okay, thank you very much.
good work. And we come to the last presentation in our session. The title is a multi-agent reinforcement learning based approach for frequency regulation of power system penetrated with dynamic RTM and microgrids. And the presenter will be presented by Ms. Lisa De Barma. She received her bachelor degree in electrical engineering from Regional Institute of Science Technology, Meghalaya, India in 2020. She completed her master technical degree in power systems in Department of Electrical Engineering at Assam Don Bosco University, India in 2022. And she is right now currently pursuing her PhD degree in Electrical Engineering Department at National Institute of Technology, Meghalaya, India. And her research interest is power system and smart grid. So you can start the presentation.
Good afternoon to everyone. Myself, Lisa De Burma from National Institute of Technology, India. Today, I'm going to present my paper on the topic entitled A Multi-Agent Reinforcement Learning-Based Approach for Frequency Regulation of Power System Penetrated with Dynamic Real-Time Electricity Market and Microgrid. Let's first start with the introduction. At first, as we know that frequency regulation will be a very important part of our life. So frequency regulation plays an important part. That means we have to maintain our frequency stability within the allowable limit, which is 50 Hz as in India, and in America it is like 60 Hz. So it is our responsibility to maintain our frequency within some allowable limit. So in order to maintain this frequency and the Thailand power deviation between the two power station, we have to always maintain the balance between supply and demand. The supply and demand will always we have to maintain. So in order to maintain the supply and demand, this mechanism of maintaining the balancing between the supply and demand can be done through a mechanism called automatic generation control, which is AGC. In power system nowadays, penetration of RES, which is renewable energy sources, has been increasing rapidly. So, which is why with the penetration of RES, our grid frequency is also lowering, and it has been an issue for us in the power system areas. So, and also plus with sudden load variation and ultimate shutdown of some generators, the grid operation may also alter the load generations balance. Which is why the frequency regulation reserve is very important. So in this context, we would like to study more further about this issue. First of all, as you can see in first block diagram, it is a block diagram of the typical control physical power system. Here you see the primary control mechanism, secondary control mechanism, real-time market, and a regulation market. First of all, if a power system has any disturbance caused and the frequency deviates within its allowable limits, the first release will be in the kinetic energy. We release our kinetic energy so that the frequency will be in it, or frequency will go back to its nominal value, which is the 50 Hz versus 60 Hz. So the second is our primary control mechanism. Primary control mechanisms works between 2 to 4 seconds. The third is the secondary control mechanism, which is also known as AGC, as I have mentioned before. In secondary control mechanism, the generator set points are set accordingly in every 2 to 4 seconds. And last is our real-time market. The real-time market that I have considered here is about 5 minutes. The 5 minutes market mechanism here has been considered using the Australian energy market operator. As of now, in Australia, the real-time market dispatches their energy power in every 5 minutes, whereas in India, it's 15 minutes dispatch time period. Here is the regulation market. What is the regulation market? In regulation market, the generator spinning reserve beats their energy. So nowadays, it's very crucial that we maintain our frequency regulation. So the market mechanism help us to maintain if any instability is in the system. As we know that RES integration is increasing rapidly, the DERs, that is at the distribution system operators, and the distribution energy resources has been opened up in avenues for the peer-to-peer energy trading between communities as well as the individuals. So in order to balance the load generation mismatch, DERs plays a very important role, that is between the TSO and DSO. These are some of the literature survey that I have been considering, and these are some of the issues that they have not considered in their work, whereas I have considered in my work, considering an advanced controller, and these are some issues in their studies. So now the next